Okay, so this is my lecture about stereo microphone techniques and recording. But even if you're interested in just recording one thing in mono, it's going to change the way you think about microphones and how you do recording. And that's the meta point of the lecture. And so the main thing that I'm interested in and why I learned this stuff, I actually first gave this presentation during a recording session to explain to the band what we're doing. And so we had a band that was playing Afrobeat type stuff. Like in this picture here is a more famous band in that style. This is Antibalas. And the point is, they're all in the room together playing live. And for certain kinds of music, but especially in my opinion, like jazz, funk, like you want it to be live, you know. And you can see that so some of those microphones aren't pressed right up against the instrument. Like above the drummer, there's a pair of overheads. And the way you record things in the studio to get a good recording is not the same as you would record live. And that's just an important thing to think about, that the trade-offs are different. At the end of this lecture, you'll understand why. Um, okay, so here's what we're going to talk about. We're going to talk about perception, how humans localize sounds, how when you hear um, one of these well done stereo recordings, you sort of close your eyes and feel where the instruments are. Then we talk about microphone perception, this sort of mechanical perception, right, with electronics and microphones and stuff. It's not the same as human perception. And then the last thing, being a recording engineer, how do I use these machines to capture the things that humans want to hear? And that's the point of this lecture. And that's sort of what the art of being a recording engineer should be. Perception is probabilistic. So you get certain information from the environment, and based on those cues, your brain is going to make the best guess about what's happening based on the available information. It's not being directly perceived, it's being inferred. And so the first thing comes from this series of experiments going back to the end of the 19th century on how humans are perceiving sound. And so you have this setup, you get your person, and you play their different sounds, and you can just ask them to point it with the sound and see how accurate they are, and you can see what their perception is, and you can play with the stimulus. This field is called psychophysics, and while it belongs to psychology, some of the best work in psychophysics is not done by psychologists, sometimes done by recording engineers or a physicist or Bell Labs people a lot of the time. And anyway, we're going to just cover that in a real high level bird's eye view, right? So first thing, you can localize the angle of where sound is coming from to within about a degree. To get an idea of what a degree is, if you hold your arm out and you look at your thumb, the width of your thumb at arm's length is about a degree. That's about how good you can do for where a sound's coming from. But you can get 2 orders of magnitude better with vision. It's much more precise to localize things in space visually. To do this localization, again, you want to manipulate the sounds people are seeing. This is another experiment that's on the roof of a building at Harvard about 100 years ago. So what are the cues? What's the information that your brain needs to try to calculate where things are coming from? And there's 3 main things I'm going to hit here. There's level, just the intensity. There's the time it takes to arrive, and there's the phase difference between the 2 ears. Level differences are the simplest thing to understand. We'll start there. Level differences mean as you move that a sound source around your head, right? Like as they're rotating the speaker around this person, you can get this graph of the perceived intensity, and you can see as you rotate on the head, kind of obviously, it's a louder at the ear that it's closer to, right? So that's just as an effect of having 2 ears at different points in space that have a different distance to the source. There's also the time difference, because the speed of sound and air is going to be more or less constant for our purposes, and so the path is different. And so if you're traveling farther at the same speed, you're going to get there at a different time. And so there's a path a difference in how far that sound has traveled to each ear, and that gives you a time difference in when that arrives at each ear. Phase differences are like time differences, but a little more subtle. And phase, one way to think about phase is the difference between a sine and a cosine wave. You have the same shape, but kind of offset in time. For the purpose of this lecture, by phase differences, I'm talking about differences where the time delay is smaller than the wavelength, than the time it takes for it to complete a cycle. This can show up one obvious way with the snare drum mic'd up like this. When you hit the drum head moves down. There's going to be a pressure increase below the drum and a pressure decrease above the drum. So these two microphones are going to have almost exactly the opposite signal, just like these two signals. Okay, so in humans, experimentally, they're only using the phase information below 1600 hertz. Again, the numbers in this lecture are pretty fast and loose, but it captures the spirit of it. But when we do the recording, we're capturing phase differences across the entire spectrum. So even though the humans are only using the phase on these lower frequencies, your recording with your microphone is going to pick up all of it. And that's going to be a big problem that we'll see throughout this lecture. The reason, though, that phase difference is not used when it gets bigger than 1600 hertz is because it's not useful anymore. It becomes ambiguous because now that phase difference for the higher frequencies is more than a half wavelength, and you're not going to be able to know what a cycle of the wave you're in, and you can't do anything useful. So that happens to correspond to the difference between your ears. They're about 15 centimeters apart, which is going to roughly give you this phase difference of 1,000 hertz. 1,000 hertz is also very roughly the frequency of that C that's above the staff in treble clef, or the often the highest note that a soprano can sing. So the point of that is the phase difference is going to be used by your brain on the fundamentals of these notes, on the lowest of the harmonics when you sound these notes, but it's not used on the upper partials, on the overtones. So you can think about what frequencies when this phase is useful for a localization. So anything above the staff, not being used. You can manipulate these three cues to simulate stereo. So if you had a very dry recording, something like a synth, you could synthesize these stereo cues to try to put these sounds in space. A lot of times when you record things, and the big lesson of this presentation, the reason I put this together for the band is to explain that I'm not doing what they think is the right way. And the right way that a lot of people think is you put your mic right up on the grill, right up in your face, right against a drum head. You get an isolated, clean, single sound of an instrument, and then you can localize them in space and add all your reverb in digitally, right? I hate that. And so that's what this talk is about, is how to do it the old-fashioned way, where you're not faking it. But one of the reasons why things are done this way, though, is not just to get that clean sound, but it's because for live purposes, and we'll come back to this when we get to the microphones, if you don't do it this way, you're going to get feedback on stage. A big reason why cardioid mics were even invented is to prevent feedback on stage. So anyway, so you have these really dry sounds, you want to put them in space, and you can do level, you can do time, and you can do phase, and all of those will give you some cues that your brain will use to figure out where these sounds come from. When you turn the panning knob on your mixer from left and right, that is only manipulating the intensity of the sound. You're just making it louder on one side and quieter on the other side. And yet this works pretty well. If you play with this on your mixer, or more likely in your software, you can hear it move from left to right. But it doesn't move in space. If you want to get a better thing in space, you can put a short delay between the left and right channels. And I'm talking about something that's less than 10 milliseconds, so it's not perceived as a delay, like the delay you would get with a delay pedal. You usually want to come up as a note value or a slap back. You want to hear the echo, so most of the standard delay effects are long. It's not what I mean. I mean a real tiny, short, precise delay between the left and the right. Again, I highly recommend doing this in your software. You can hear what it sounds like. This will give you a different effect than just turning the knob on your mixer. You can play with phase, and most of the mixing boards and the software are going to have this phase button, which is just going to flip things by 180 degrees. But you can also build a device that will actually change the phase between the two signals. And so if you had a 1960s electronic music studio, you would buy this box and you can play with the phase and you can make things move from left to right. It's a different perceptual effect. The goal of these recording techniques is to capture all of these cues naturally from the live performance using microphones. And now if you look at pictures of classic recordings, so here's the Dave Brubeck trio, here's Stevie Wonder, here's a classical recording. You look at any of these, the microphones are not right up against the horn, it's not right up against the drum kit. Those mics in this picture, like Stevie is singing into one mic, but all those horns are being picked up by group ensemble mics for the whole horn section, not one horn shoved down the bulb of each horn. Classical recordings have always and only been done this way. You have a small number of mics because you want the sound of the orchestra. And so when you are doing these kind of recordings, when you're figuring out, how to get the sound of the trio with a handful of mics, or do a classical recording with maybe just two mics, maybe you're a BBC engineer, and you're like a real recording engineer, like a school doing math, you're designing these systems, you're trading the cues off against each other. And so you're saying that level, intensity, time, phase, all these things, you want to design a system that will measure them. So let's talk about microphones and how microphones work. So you've all used microphones. You probably know there's a right end to sing into, but I want to talk about how that works. And if you look at the old ads for these cardioid mics and you read the copy in these ads, they are designed, mostly they're sold because, like this one here on the left, true cardioid performance cuts reverberation and random noise pickup, stops feedback, excellent for high quality public address. Over here on the right with this Shure mic, it says the perfect microphone choice for use with PA systems. Cardioid mics are designed so that they won't hear the stage speakers, so they can't feedback. That's why they're made and sold, but there are compromises there. Okay, so next thing to define is this idea of a polar pattern. You want to know what the microphone is hearing based on the angle of the sound source from that microphone. So you can put that in polar coordinates. You want to know that angle, and then you can sweep, go around, just like that plot of the sound moving around the person's head. You can make a plot of the sound moving around the microphone, and you can say, this is where the sound's coming from. One thing to keep in mind, I really like this figure, because usually you only see that picture on the right of the polar pattern, is kind of top-down view. But remember that the microphone is symmetric. It's a 3D. And so that a cardioid pattern now looks really different in 3 dimensions. But this is what the microphone hears. Okay. The way these are engineered affects what the microphone hears, and there are different kinds of microphones that have different sort of polar patterns. Microphone has a moving part, whether it's a diaphragm or a coil. And usually when you go to buy microphones, you talk to recording engineers, they're going to talk about the way they sense that movement electrically, whether it's a condenser mic or a ribbon mic or a dynamic mic, it's talking about how it's sensing the moving part electrically. But what's more important is how that moving part is exposed to the atmosphere. Remember that a sound is a variation in air pressure, and that's what the microphone is designed to capture. The most basic thing you can do, right? You have your moving part and you seal it off behind it. This is just giving you a pressure sensor. The pressure sensor picks up sound in all directions equally. It's an omnidirectional microphone. It's a circle, or about as a spear around your mic, right? This is also one of the first things that you would invent if you were trying to invent microphones from scratch. The next thing, and this is now like 1930s technology, is this idea of a pressure gradient microphone. Electrically, it's different, but that doesn't matter. The important thing is that moving part you see on the left in the center, that ribbon, is open at both sides. So this is actually sensing the difference in pressure from front to back. You can think about it as like a paper plate, right? If you have that a plate like round, like high to your face, like you're playing a peekaboo, you're blowing to the plate, you will feel it move. If you turn that plate, if you feather it so it shrinks, so it just collapses down to a line, and you keep blowing, you won't feel that plate move. And it's the same thing with ribbon mics. And they have this figure eight pattern where if you're, have like that plate feathered with that ribbon, you're looking like right down it, so it's as thin as possible. You can't move it. There's no difference. But if you're on the front or the back, you are able to move that ribbon, and you get this figure eight effect. One of the great things about figure eight mics is they have a much tighter rejection. So if you talk into the side of a figure eight mic, it will probably not be picked up. It has much better performance than a lot of cardioids. The other thing is that the front and back, because this thing is moving forward and back, is going to be out of phase. Now, how do you make a directional microphone, right? We've seen that if you have your capsule open on both sides, it's picturing this gradient. And if you have it sealed off at the back, you get an omni. If you put both of them in the same box, you can electrically combine them to get a cardioid shape. And so, I have this monoprice mic, and that's basically how it works. It's actually a little more complicated than diagram, but basically you have an omni and a figure eight, and when you add them, it adds in the front. It gives you more pickup from the front. It's like reinforcing, and it cancels in the back because they're out of phase. That's how you get the cardioid shape. You can make this happen electrically. It's also designed as this classic RCA mic. You can also make this happen acoustically. So if you look at some of these condenser mics, I have some mics that are like this. That little thing on the end unscrews, and you can get different polar patterns by changing the capsules. They're actually all the same sensor. It's just the acoustic properties that change it. So the Omni mic, like I said, it's sealed, right? It's a pressure sensor because it's in all directions. But the cardioid capsules and the hypercardioid capsules, which is just a tighter cardioid, they have these vents at the back. And so sound's coming in from behind the sensor and bouncing around in there, and acoustically, it's canceling that signal from the rear instead of doing it electrically, like in that old RCA mic. But you're getting the same effect. That acoustic cancellation is producing that cardioid pattern. You can prove this to yourself, by the way. If you take one of these cardioid tape mics, you can just take some masking tape, tape over all those little holes, and it will become an Omni mic. And I have the gear if you want to convince yourself. These cardioids, you have this kind of heart-shaped pickup pattern, right? But it's not actually true. So the directional mics aren't perfect. And at lower frequencies, they are less directional, and they become more and more like an Omni mic. So that cancellation is going to be the amount to which it cancels is different at different frequencies. And so if you now plot the polar pattern by frequency, what you'll see over there on the right, for the high frequencies, it gets tighter and tighter and more heart-shaped. And on the left, the frequencies get lower and lower, it gets more and more Omni. One consequence of this that's bad that happened in that recording that I made when I made these slides is all the bleed gets into the mics from all across the room. So every mic has bass. And so that's the last time I recorded a bass amp. And from now on, the bass player goes direct because every mic hears the low end. A cool thing, though, is if you know that your microphone is doing that, you can tilt it off axis, right? So if you look at the writing on these high frequencies, you can see that if you pointed right down the center of the mic at 0 degrees coming in from the right on this diagram, you're going to get everything. But as you move off axis, you're going to lose the high frequencies first. They're being canceled. And so if you have an electric guitar mic and you move it at an angle, you can lose some of that high end. Sometimes people will do that when you have a kind of bright, sharp electric guitar sound. You can move the mic a little bit to the side of the speaker and get a darker sound. Like knowing how your mics are made and how they hear will let you move the mic to get what you want without having to do any electrical stuff whatsoever. Okay, so time, phase, and level differences matter for perception. Microphones have different pickup patterns: omni, figure eight, and cardioid. Now we're going to put those together to record in stereo. We're going to use more than one microphone to try to pick up these three cues so that when you listen to the recording played back, you have this stereo perception. So the rest of this lecture is about how to do that. And I'm going to start with the most basic thing and the first thing that you would think, and this is also the first thing that they thought of at RCA and Bell Labs, AB, spaced pair. So you get these two mics. They're far away from each other. And now just looking at it and thinking about it, you're going to get these intensity differences, just like having how your two ears are different. Those two mics have a different path length to each drum, so they're going to get different intensity. They're also not in the same place, so you get different time cues. And that should be good. You have this, you have the arrival time, you get time, phase, and level. So we're done, right? Like, there's no need to invent anything else. The problem is, if you combine the signals from those two mics, all the phase information is going to get canceled. And so, like I said, if you have this mic on the top and bottom of the drum and you add them together, you're not going to hear very much. And what you're going to get is comb filtering. So at certain combinations, these frequencies are going to cancel. If you want to know what comb filtering sounds like, you can just take your delay plug-in or whatever and set it for some really short thing, and you get this kind of hollow metallic sound. If you think of flanger or phase shifter, they're doing this, but then they're moving the peaks up and down, so you get this kind of swirling. That's fun, that's cool. But when it's like static, it just sucks. It's just a bad recording. And if you're doing vinyl, it's even worse, because if you have big differences in the left and right a signal, you're actually going to fall out of the groove. So it's important to not have too much difference between left and right, especially on those low frequencies where all the power is. When music is played back live, it gets collapsed to mono. And so you can think about this if you have like a sound system with subwoofers, or a lot of times music being played in informal environments like boom boxes and sound systems, or even these little Bluetooth speakers. All of these are mono devices. Mono compatibility still matters, even though people have nice stereos now. Okay, so how do we avoid these phase problems? How do we avoid getting that kind of weird, nasty sounding comb filtering effect? So the phase is being picked up by having the microphones distant from each other, right? But if you take that distance between your two mics, that H, and you put them in the same spot, that H collapses to zero. The path to each microphone is the same, sound right at the same time. There's no more phase cancellation if you mix it down to mono. You can do this, and this is one of my favorite things to do. and have the two mics in exactly the same location in space. But there's a trick. You can still get a stereo effect even though you don't have any phase information. And so the trick is to use directional mics so that as you move around the room, you're getting a different amount of intensity in each mic. So you are not getting time differences. You're not getting phase in the same place, but you're getting intensity. Intensity is enough to do stereo localization. One way to do this is called the Bloomline pair, where you have two figure-8 mics at 90 degrees to each other, often with a pair of ribbon mics. And you can see you have these two figure-8 patterns, and then they're on, right on top of each other. And so you're getting these intensity differences, but no phase differences, no phase cancellation when summed to the mono. You will not get phase problems because you designed your sensing system such that you never measured that information. It works very well, and these recordings sound great. And there's a nice paper you can read about it by Michael Gerson. But also, I've seen the same paper that he wrote here several times, where people take two mics and they try it, and it sounds so good that you wonder why you would do anything else, because it can sound better than a more complicated recording. I wanted to say that again because I don't think enough people know this. If you do these simple two mic old school recordings, they can sound better than recording each instrument individually and then trying to put things back together by using all your electronic wizardry. It can be cool, but it's not going to be the same as just the band playing in the room. If you don't have a figure-8 mics, you can use cardioids and have them in the same place. And some people will call this XY. I have a classical recording that I did this way if you want to hear what it sounds like. It's similar to the Bloomline, but these microphones are still directional. So you're only going to get what's in front of them, and you're not going to get the back of the room. So the classical recording that I did this way, it's very crisp. It sounds very commercial and very bright. It has a lot of detail, but it doesn't have as much reverb because you're still ignoring half of the room. With the Bloomline, you're going to get the whole room. And so these things, by the way, it's a caveat in the whole thing. It's only going to work if the band sounds good and then a room that sounds good. Then you get a recording that sounds good. Garbage in, garbage out. Okay, so anyway, these cross mics in the same place, it's called XY. Here's another example of how you would set this up with these directional cardioid mics. And I had a slide that said that, okay. So because you're not getting what's behind you, you're not getting as much of the sound of the room. There's another whole set of techniques called near coincident. So if instead of doing on the left where the mics are right on top of each other, like in this XY, they're literally right on top of each other. If you move those mics apart, you're going to start getting phase information. So if you're in a situation where you don't care about the phase cancellation, you can do that, and you're going to get a little more information. You're going to get more stereo cues by moving your mics apart, but you're going to break that compatibility when you're summed down to mono. These near coincident techniques are very popular for classical music or drum overheads, and they have these complicated acronyms because a lot of state-run broadcasting organizations, like the French equivalent, the equivalent of the BBC, will design this technique and they'll write a white paper on it, and they'll be like, when you record orchestras, you put the mics like this, you get consistent, good results. Okay, so here, this is ORTF. See the mics are crossed at 110 degrees. The capsules are spaced 17 centimeters apart. And again, because they're not in the same place, just like your ears, which are spaced 15 centimeters apart, that's not a coincidence. That's why it's done this way. You're going to get the intensity differences. You're going to get the time differences. You're going to get the phase differences. These can make great sounding classical recordings or drum recordings. This is the the Dutch or the German standard, depending on how far away, but these are at a 90-degree angle. You can see they're facing away from each other. And the idea is you have your microphone array like this, and you point the center of it, the center of your stereo image, you point that at the center of the ensemble, and then everything comes out in the right place. By the way, if you're doing classical recordings, part of how classical music is written and meant to be perceived, things have to be in the right place. So you can't play games. And so if you look at the seating in an orchestra, it's always the same way, and it's for a reason. And if you start moving the players around, or moving the players around, post hoc with playing electronic games, it's not going to sound the way the composer intended it. So classical recordings need to be done in this very exact way without any wizardry. So there's one problem with these, though, that makes them sound different than when you hear stuff. And that's you don't just have ears, you have a head. And your head is blocking the signal between the mics. And so one way you can get this effect is to be super literal minded and build a head with ears and then put little mics in them. What's happening, if you go back to that plot where I move the sound around your head, you can do it again, but be a little more clever. And the stimulus that you're giving to the person, you can change the frequency. And now you can make this plot, as I move the sound around your head, how does the intensity change as a function of the frequency? And now the point about all these little plots is they're not the same. So your head will be blocking more or less of the sound as you change the frequency of that sound. So your head has a complex effect. In fact, if you model it, people doing video game sound, synthesize things, call this thing called a head-related transfer function, where you can try to actually figure out what this function is. But because we're doing low-tech recordings, we're just going to do something else to block signal between the mics. My favorite technique for doing this is called the Jeckin Disc. And this is a beautiful paper. And it proceeds from first principles. This is what I want, and here's how I'm going to get there. And so what he wants to record with Omni microphones. And the reason is all cardioid mics are compromised. All cardioid mics have this problem that the directionality changes at the frequency. But Omni mics are totally flat. Omni mics hear the same thing in the same direction for the same amount at any frequency. Omni mics are sort of, you can think of as cleaner and better. But they're Omni mics. They pick up everything. So you can't record classical music with Omni mics because you get the whole room. So what the Jeckin Disc does is it spaces the mics apart and then has this disc in the middle that blocks the signal, just like your head blocks the signal between the two sides. So what you're going to pick up with that, you're going to get time differences, you're going to get phase differences, you're going to get the same level differences between the mics, but now it's going to vary with wavelength, just like it does as sound moves around your head. So my brother and I built one of these. I have a recording of him and a pianist, actually, and he recorded it several times with the same mics in the same room, different ways. And I can tell you that this sort of homemade Jeckin Disc we made out of cork and felt and I think bicycle parts and foam. This thing sounds great, but it sounds very different than using just the cardioid mics, because with the same mics, with the same caps on the end that screws on, the Omni mic, you can just look at the chart for this actual mic, goes totally flat. And so the Jeckin Disc recording compared to the cardioid recording is darker because you're picking up more of the low frequencies. The Jeckin Disc recording also, remember these are Omnis, you get in the whole room. It's just great. If you like 1950s classical recordings that have this kind of like darkness and kind of sound like it's in a room in a space, this is just a wonderful thing to do. And I can't say enough good things about it. For $100 mics, we got a recording that's worth more than $100. That's the point. Another thing you can do in a similar vein, if you have figure 8 mics, we talked about doing the Bloomline pair, where you're going to have these two mics cross at 90 degrees, and you're going to send one to the left and one to the right. But there's something even cooler that you can do, which is I'm going to explain it first, saying we have a cardioid mic and a figure eight mic. And so we'll take that cardioid mic for what we call the center channel. You're going to point that right at the band. And then your figure eight mic is perpendicular to the band. So it's only picking the sides, and that the center, that null, that thing the figure eight mic can't hear, is pointing at the band. Here's why. When we mix it, now we're going to do a couple electrical tricks, but they're analog tricks. So you're going to take these two mics and you're going to combine them. And so first on the right, you're going to take the center mic and then a side mic, and you're just going to add them. But the figure eight mic is recording things out of phase. So when you add those two together, you're going to be removing information coming from the left, canceling it because it's out of phase, and increasing, reinforcing it because it's in phase on the right. When you mix the left channel, you're going to subtract the side mic from the center mic. Now, all that stuff that I just said canceled because it's out of phase. Now it's in phase, it's reinforced. Everything that you got on the right when you add things is now lost because it's now out of phase. Another way to think about what you're doing with the mid side, if you look at the top, right, we have this cardioid and figure eights, and at the bottom, this is what the sum and difference signals look like. You're basically steering the mics, but you're steering them electrically by deciding how much to combine the center channel with the side channel. So this is a way you basically can effectively move the mics, but after the recording has been done. This is the only technique that lets you do that. It's mid-side. When you add the channels back together to produce a mono signal, because both the left and right have the mid channel, when you add them, they're in phase, you get it. But those sides, because you added it to the left channel and you add it to the right channel, you subtract it from the left channel. When you add those together, you have like A plus B, and you have A minus B, and B cancels out, you only get 2A. That's what happens. That's the mono compatibility is only that center mic. It's perfect mono. And this is also how FM stereo works. And it lets you adjust the width, unlike any of these techniques. So if you just, as you turn that side mic down, you're getting more of the center. If you turn the side mic up, you're getting more of the side. So just by a simple analog control, you can shape the recording after you've done it. If you do mid-side with a figure eight mic, it's a little easier to see. The way those polar patterns combine, your two figure eight mics, now one figure eight mic is pointed straight at the band, and the other figure eight mic is perpendicular to the band. As you add them, effectively, if you could plot the polar pattern of the left and right channels as you mix in more of those two mics, you're actually just rotating the mic around its axis. So imagine you had your figure eight mics in the room, and you could just turn them until you hear the sound you want. Well, if you did it mid-side, you can do that as you're mixing. And again, it's all analog. There's no fancy processing. It's just adding and subtracting signals. All of this, not just this, but also 30 other things, is in one patent written by Alan Blumlein while he was working for the BBC for a few weeks in the 1930s. Absolutely incredible. Okay. You can also design mics. So this is a very high-end stereo mic. It has the two figure eight mics crossed and one omni mic, all in one vertical plane. So if you buy a mic like this, you can just get it and point at your band, and later, as you're mixing, as you're combining the mid and the side, you're basically designing sort of the pickup pattern you want with these pair of like virtual microphones that you're synthesizing, again, just in an analog way. Mid-side recording is kind of hard to grasp, but the point is that it's super powerful and super cool and super easy. You get your two mics, and one of them should be a figure eight that's not pointed at the band to get the sides, one mic down the middle to get the band, and as you mix them, you're basically rotating these mics virtually. Again, that's amazing. I highly recommend trying it. You got to set up the mixer in a certain way, but it's definitely worth doing. So here's the point. The stereo perception, we started with what humans hear, if level differences, phase differences, and time differences. Microphones have different sensitivities to sound from different directions. And in particular, we covered having an omni mic, which is sealed. It's a pressure sensor. It gets the same sound from all different directions. We have a cardioid mic, which you've probably used before. It's sensitive to the front and not so much to the back. We have a figure eight mic that's sensitive to the front and back and not to the side. Moving the microphones around and choosing it by the polar pattern allows us to pick what cues we want to capture. If the microphones are right on top of each other, you've eliminated the phase and you're just playing with the intensity. And so that would be true of, say, the figure eight recording, blue line recording, XY recording. Just intensity is enough to have something that sounds like it's a stereo that still sums down to mono. If you move the microphones apart from each other, you start picking up phase information. That can sound good. I would recommend it for a classical recording, for example, but if it's going to get summed down to mono, it might sound really bad when you put it together. Another thing that can happen, I did this by accident once, you can take your signal when you're mixing and put it out of phase in the left and right. Some cheap synthesizers that I had in the 80s had this trick to make them sound stereo, but they're not really stereo. They just cross the wire on the jack, right? And so they're the same signal left and right. They're just out of phase. On the headphones, all this phase stuff sounds super wide and big. And I had a rock song I was doing, and I took the guitar and I had it left and right out of phase, and I was kind of lazy, and so I didn't want to double a track. I was like, I'll just put it out of phase. It sounds fine on the headphones, and I play it through my Bluetooth speaker. The guitar is totally gone, totally cancels because of the phase. Like, at least if you get nothing else, anything you do, push the mono button on your mixer or in your computer, and make sure that you didn't cause all these phase problems. Once you know what they sound like, you can avoid them at the capture of the sound, which is the best way. There's nothing to fix if you record it right going in. If you put the microphones on top of each other, you will not have phase problems, and I strongly recommend at least considering that when you design your recording. And we talked about some of these methods for capturing stereo cues. Don't bother to go back and memorize them. There's a handout that I'm from a microphone manufacturer that has what all these things are, like what the details on how to set it up, and some idea of how they sound, which is kind of interesting. So on the right, these coincident ones, they're only getting the intensity information, right? So when it goes down to, say, spaciousness, often rather limited. Well, you've only got one of those cues, so you're not getting as strong a stereo sensation. But at an engineering point of view, it's the best way to do it. If you have the mics moved apart a little bit, or you use a Jeckin Disc, you get nice spatialization. And if you move the mics super far apart, you get a very big, wide sound. You might not be able to tell where things are coming from. And you can think about doing this with a drum set, but it's going to make the drum set sound like your head is 20 feet across. It's not a natural sound, but it could be a cool sound. If you're making, Led Zeppelin kind of band, you maybe don't want it to sound like a jazz band. It's okay to have drums that are 100 feet wide. I talked about phase, microphones. That's kind of the end. So we went back where we started. how do you localize sound? How microphones hear? You do stereo recording by moving the microphones around to capture those cues that humans use to localize sound. And please worry about phase. Thank you.